Our goal is to find the pH of different salt solutions, and we'll start with the solution of sodium acetate. So in solution, we're going to have sodium ions, Na+, and acetate anions, CH3COO-. And the sodium cations aren't going to react with water, but the acetate anions will. So the acetate anion is the conjugate base to acetic acid. So the acetate anion is going to react with water, and it's going to function as a base. It's going to take a proton from water. So if you add an H plus to CH3COO-, you get CH3COOH. And if you take a proton away from water, if you take an H plus away from H2O, you get OH-, or the hydroxide ion. All right, so let's go ahead and write our initial concentrations here. So our goal is to calculate the pH of our solution. And we're starting with 0.25 molar concentration of sodium acetate. And so that's the same concentration of our acetate anion here. So we're going to write 0.25 molar for the initial concentration of the acetate anion. And if we pretend like nothing has reacted, we should have a 0 concentration for both of our products, right? So a 0 concentration for our two products. Next, we think about the change. So CH3COO-, the acetate anion, when it reacts, it's going to turn into CH3COOH, or acetic acid. So whatever concentration we lose for the acetate anion, we gain for acetic acid. So if we make the concentration of the acetate anion X that reacts, right? So if X reacts, if X concentration reacts, we're going to lose X, and we're going to gain X over here. Right? It's the same thing for hydroxide. We would be gaining X, a concentration for the hydroxide. So at equilibrium, the concentration of acetate would be 0.25 minus X. So we're assuming everything comes to equilibrium here. The concentration of acetic acid would be X. The concentration of hydroxide would also be X. All right, next we write our equilibrium expression. And since this is acetate functioning as a base, right, we would write Kb here. So we write Kb is equal to concentration of our products over concentration of our reactants. So we have the concentration of CH3COOH times the concentration of hydroxide, so times the concentration of OH-. This is all over the concentration of our reactants, and once again we ignore water. So we have only the concentration of acetate to worry about here. So we put in the concentration of acetate. All right, so let's think about the concentration of acetic acid at equilibrium. Right, so at equilibrium the concentration is X. So I go over here and put X. And then for hydroxide, it's the same thing, right? The concentration of hydroxide at equilibrium is also X. So I put X in over here. And then for the concentration of acetate, right, at equilibrium, concentration of acetate is 0.25 minus X. So 0.25 minus X. Next, we need to think about the Kb value for this reaction. And you will probably not be able to find this in any table, but you can find the Ka for acetic acid. So acetic acid, right? Acetic acid and acetate is a conjugate acid-base pair. And the Ka value for acetic acid is easily found in most textbooks. And the Ka value is equal to 1.8 times 10 to the negative 5. And our goal is to find the Kb, right? What is the Kb for the conjugate base? And we know that for a conjugate acid-base pair, Ka times Kb is equal to Kw, right? The ionization constant for water. So we can go ahead and plug in 1.8 times 10 to the negative 5 times Kb is equal to, we know this value is 1.0 times 10 to the negative 14. So we just need to solve for Kb. So we can get out the calculator here and take 1.0 times 10 to the negative 14. And then we divide by 1.8 times 10 to the negative 5. And so we get 5.6 times 10 to the negative 10. So let's get some more space down here and let's write that. So Kb is equal to 5.6 times 10 to the negative 10. And this is equal to x squared, right? Is equal to x squared over 0.25 minus x. Next, to make the math easier, we're going to assume that the concentration x is much, much smaller than 0.25. And if that's the case, right, if this is an extremely small number, we can just pretend like it's pretty close to 0. And so 0.25 minus x is pretty much the same thing as 0.25. So let's make that assumption, once again, to make our life easier. So this is 5.6 times 10 to the negative 10 is equal to x squared over 0.25. So now we need to solve for x. All right, so we have 5.6 times 10 to the negative 10, and we're going to multiply that. We're going to multiply that by 0.25, and so we get 1.4 times 10 to the negative 10. So we now need to take the square root of that number, right? And we get x is equal to, gives us x is equal to 1.2 times 10 to the negative 5. So let's go ahead and write that here. So x is equal to 1.2 times 10 to the negative 5. All right, what did x represent? Right, we have all these calculations written here. We might have forgotten what x represents. X represents the concentration of hydroxide ions, right? So x is equal to the concentration of hydroxide ions. So let's go ahead and write that down. X is equal to so this is molarity. This is the concentration of hydroxide ions. And if we know that, we can eventually get to the pH, right? That was our original question. Calculate the pH of our solution. So we could find the pOH from here. I know the pOH is equal to the negative log of the hydroxide ion concentration. So I can take the negative log of what we just got, so the negative log of 1.2 times 10 to the negative 5, and that will give me the pOH. Right, so let's go ahead and do that. So the negative log of 1.2 times 10 to the negative 5 is going to give me a pOH of 4.92. Right, so I go ahead and write pOH is equal to 4.92. And finally, to find the pH, I need to use one more thing, because the pH plus the pOH is equal to 14. Right, so I can plug in the pOH into here and then subtract that from 14. So the pH is equal to 14 minus 4.92, and that comes out to 9.08. So the pH is equal to 9.08. So we're dealing with a basic solution for our salt. Let's do another one. So our goal is to calculate the pH of a 0.050 molar solution of ammonium chloride. So for ammonium chloride, we have NH4 plus and Cl minus. The chloride anions aren't going to react appreciably with water, but the ammonium ions will. So let's write our reaction here. So NH4 plus is going to function as an acid. It's going to donate a proton to H2O. So if H2O accepts a proton, that turns into hydronium ions, so H3O plus. And if NH4 plus loses a proton, we're left with NH3. All right, so let's start with our initial concentrations. Well, we're trying to find the pH of our solution, and we're starting with 0.050 molar solution of ammonium chloride. So that's the same concentration of ammonium ions, right? So this is 0.050 molar. And if we pretend like this reaction hasn't happened yet, our concentration of our products is 0. Next, we think about the change. And since NH4 plus turns into NH3, whatever we lose for NH4 plus is what we gain for NH3. So if we lose a certain concentration of X for ammonium, right, if we lose a certain concentration of X for NH4 plus, we gain the same concentration X for NH3. And therefore, we'd also gain the same concentration for hydronium as well. So at equilibrium, our concentration of ammonium would be 0.050 minus X. For the hydronium ion, it would be X. And for ammonia, for NH3, it would be X as well. So we're talking about ammonium acting as an acid here, and so we're going to write an equilibrium expression. We're going to write Ka. So Ka is equal to concentration of products over reactants, so this would be the concentration of H3O plus times the concentration of NH3, right, all over the concentration of NH4 plus, because we're leaving water out, so all over the concentration of NH4 plus. All right, the concentration of hydronium ions at equilibrium is X, so we put an X in here. Same thing for the concentration of NH3, right? That would be X, so we put an X into here. This is all over the concentration of ammonium, which is 0.050 minus X. So over here we put 0.050 minus X. Next, we need to think about the Ka value. Right, so finding the Ka for this reaction is usually not something you would find in a table in a textbook. But we know that we're talking about an a conjugate acid-base pair here. So NH4 plus and NH3 are a conjugate acid-base pair. We're trying to find the Ka for NH4 plus. And again, that's not usually found in most textbooks, but the Kb value for NH3 it's 1.8 times 10 to the negative 5. So for a conjugate acid-base pair, Ka times Kb is equal to Kw. So we're trying to find Ka. We know Kb is 1.8 times 10 to the negative 5. And this is equal to 1.0 times 10 to the negative 14. So we can once again find Ka on our calculator. So 1.0 times 10 to the negative 14. We divide that by 1.8 times 10 to the negative 5. And so the Ka value is 5.6 times 10 to the negative 10. So if we get some room down here, we say Ka is 5.6 times 10 to the negative 10. And this is equal to, this would be x squared over here. And once again, we're going to assume that x is much, much smaller than 0.05 and 0. So we don't have to worry about x right here. If it's an extremely small number, 0.050 minus x is pretty much the same as 0.050. So we plug this in and we have 0.050 here. So we need to solve for x. So we get out the calculator and we're going to take 5.6 times 10 to the negative 10, and we're going to multiply by 0.05, and then we're going to take the square root of that to get us what x is. So x is equal to 5.3 times 10 to the negative 6. So x is equal to 5.3 times 10 to the negative 6. X represents the concentration of hydronium ions. So this is a concentration, right? This is the concentration of hydronium ions. So to find the pH, all we have to do is take the negative log of that, right? So the pH is equal to the negative log of the concentration of hydronium ions. So we can just plug that into here, 5.3 times 10 to the negative 6, and we can solve. And let's take the negative log of 5.3 times 10 to the negative 6. And so we get 5.28 if we round up here. So let me get a little bit more room. So we're rounding up to 5.28 for our final pH. So pH is equal to 5.28. So we got an acidic solution, which is what we would expect if we think about the salt that we were originally given for this problem.